Okay, so welcome back to another session. Please, do you have any questions for me before we start? Okay, perfect. So then let's get on to where we started from. Let me try and admit some people and then. Okay, I'm sharing my screen. Please, if you can't see, do let me know. Last time on 2.3. Okay, so the last thing we looked at was 2.3, right? We were on question B, right? On question P. So example 1, question B. So we started looking at, we were asked to find the limit as x approaches 1 of f of x times g of x, right? Wait, there's something with the selecting thing. Okay, give me a sec. 2.3. Control function F5. Shift function F5. Okay, yeah. So I'm here, right? So you're trying to look at part B, right? That was the example we're looking at. So for this one, let me go to the whiteboard. So this 2.3. 2.3, and then this is example 1. On slice. So we're looking at part B, right? So part B asked us to find the limit as s approaches 1 of f of x. Oh, what's happening? Of f of x times g of x. Okay, so from the limit laws that we learned the last time, we said that the limit of a product of functions is equal to the product of the limits, right? If the limits exist. So with this one, we tried by starting to split this up as the product of the limits as follows. So we did limit as s approaches 1 of f of x times the limit as s approaches 1 of g of x, right? That's what we started with, right? Okay. And then we went back to the graph, right? So let's go back to the graph. Let me share my screen. Please, I'm back on a PowerPoint. If you can't see, do let me know. So on the graph, we realized that in part B, we needed the limit as s approaches 1 of f of x. And we saw that that was 2, right? Because if you track the function from the left and from the right, you are getting to this point, which is 2. On the other hand, if you track the g of s function from the left and from the right of 1, then you notice that they are not the same, right? Because from the right, you are approaching this point here, which is -1. And then from the left, you are approaching this point here, which is -2. So the two limits are not the same, right? The two one-sided limits are not the same. So that means that the two-sided limit, right, in general, as you approach 1, it does not exist, right? So it's DNE. So that means you encounter something like 2 times DNE. And as I said, you can't multiply 2 by a number that does not exist. So when you get to this point, you're actually stuck. So what do? Well, we learned from 2.2 that whenever you are trying to find a limit and you are stuck, then your best route will be try and take the one-sided limits, right? So take the one-sided limits, and if they agree, then that means the general limit or the limit as you approach a number will be that number, right? Will be that answer. Will be that answer. So we started by finding the one-sided limits. And as I said last time, the laws that you learn, right? The laws that you learn for the general limit also apply to the one-sided limits, right? The same laws apply to the one-sided. So that means for this one, the limit of a product of functions under the one-sided limit will also be the product of the limits. So we have something like so. And then with that one too, from the right, right? So from the right to, we will have the limit as s approaches 1 from the right of f of x times the limit as s approaches 1 from the right of g of x. You have these, right? And these ones we're able to obtain. For the limit as s approaches 1 of f of x, 1 from the right of f of x, that one we got 2, right? So you're getting 2 times. What about the limit as s approaches 1 from the right of g of x? That one was -1. So in the end, you are getting -2, right? That's from the right. Now, we also follow through and get from the left, right? So from the left, we have this, the product of the functions. And then for this limit, this would be a product of the limits, right? So we do from the left of f of x times the limit as s approaches 1 from the left of g of x, right? Now for the limit as s approaches 1 from the left of f of x, we saw that to be 2. Because the general limit is 2, I mean, if you approach from the right or from the left, it's also going to be 2, right? So that's 2. And then for this one, we had it to be -2. So that means you are getting -4, right? So from here, you can see that the limit as s approaches 1 from the right of the product of these two functions, and then the limit as s approaches 1 from the left of the product of the two functions, they are not equal, right? So because they are not equal, you can therefore conclude that the limit as s approaches 1 of the product is what? Is DNE. It does not exist. Please, are you okay? Yeah, so please don't do operation like 2 times DNE is DNE. No, it's incorrect, right? Whenever you get stuck, you have to try the one-sided and see, right? So that's it on that. Please, any questions here? Are you okay? Okay. Now, anybody needs time here? Okay. If you don't need time, then let's go back to the PowerPoint. So the next question is C, right? So for C, you're trying to find the limit of a quotient of function. So f of s over g of s as s approaches 2. As s approaches 2. So let's try that on the whiteboard. You're approaching 2. So let me move to the next. So C, limit as s approaches 2, f of x over g of x. Okay, so for this one, applying the limit laws, the limit of a quotient of functions is the quotient of the limits, right? And we don't need the denominator to be 0, right? The limit of the denominator to be 0. But then let's see what's happening here. So from this one, we can move to this step. This will be equal to this over the limit as s approaches 2 of g of x, right? So that's one step. Now let's go back to the graph and then try and figure out these limits and see, right? So I'm going to go back, but please, you need time on this. Okay, I'm going to go back to the PowerPoint. We need to read 2 limits, right? All of them are approaching 2. So let me go back here. So for C, we need 2 limits. We need this and this. And could you please help me out here on this one? What's the first one and what's the second? As I said, your responses are always appreciated, right? Your contributions are always appreciated. So please speak your mind. What do you think these will be? Can anyone help me with anyone? For the first one, what do we get? What's the limit as s approaches 2? Perfect. I see something in the chat. So I see 1.5. Okay. So generally approaching 2, 1.5. Okay. So I have a second to 1.5. So let's see if this is true. So for this one, let's see. Limit as s approaches 2. We are looking at f of x. So we are looking at this one, the top graph, or the kind of like the red graph here, right? So for this, as we approach 2, locate 2. Where is 2? 2 is somewhere here, right? 2 is somewhere here, 2. So we are tracking this function. So from this side, from the right and from the left, you can see that they are all approaching this point, right? So this point is somewhere 1.5, 1.4. Yeah, so I agree with you. So I can say this approximately, say 1.5, right? So somewhere 1.5. Yeah. In the book, in this question, it used 1.4, but that's not going to make any difference here in this case, as you see shortly. Okay, so now we are done it for the f of x. Can anyone help us with the g of x? What's the limit as x approaches to of g of x? Anybody? Okay, so I have 0. Thanks, Daniela. Yeah, 0, 0. Okay, so I have a seconder to 0. Thank you guys so much. Yeah, Kenzie. Perfect. Okay, so yeah, I agree with you, right? So for the g of x, the limit of g of x as x approaches to, since the g of x is the blue line, you're just focusing on the blue line, right? And you're approaching 2 from the 2 sides, because this we are approaching for the 2 sides. So I'd say I looked it up and it turns out we can just call it 2-sided, right? So you see that you are using the limit or 2-sided. Someone is coming in. Okay. So for this one, you approach it from this side and from this side. And then you can see it's approaching this point, which is what? It's just flat on the x-axis. And that is going to be 0, right? So that's 0. Perfect. So that means in our case, going back to the whiteboard, this is like 1.5 over 0. So you have a what? A non-zero number. You have a non-zero number over 0. Do you see? And this is something that we learned in 2.2. We learned how to do this, right? Now, whenever you're taking a general limit and you hit a and you get to a part where like you evaluate it and you get a non-zero number over 0, then what you have to do is to what? Is to do one-sided, right? So let's do the one-sided, because for the general one, the possible answers are either infinity, negative infinity, or dne. You will end up writing one of these, right? So let's see which one it is. Now, as I said, infinity and negative infinity don't mean they exist, right? They are all types of dne. But when they occur, we write them rather than dne. Please, are you okay? And dne is a more general case. It includes the case whereby it's infinity. It includes case whereby a function is oscillating between points. It also includes a case whereby the left-hand limit and the right-hand limit don't agree, and you're trying to take a general limit. That one will also be dne, right? So for this one, let's see. For this to take from the right and then from the left, right? Okay. So from the right, since the general one is 1.5 for the top, we know that one is approximately, as I said, the 1.5 is an approximate value. The slide used 1.4, right? It's just an approximate value, and nothing will change with the 0.1, right? So over this. Now for this one, as you can see, if you're approaching from one-sided, then we're either going to get an infinity or negative infinity. But you just have to figure out which side of the 0 is approaching from. Is it approaching 0 from the right? In other words, is this kind of like a 0.0001, or is it approaching 0 from the left? In other words, is it a negative 0.001? So that's what you're going to figure out. So you're looking at 2 from the right, right? So let's just go back to the PowerPoint and then try and figure out what the g of x is approaching, whether it's approaching 0 from the right or from the left when you're approaching 2 from the right, right? So that's what you're going to do. Please, anybody needs time here? Okay, so then I'll go back and then see 2 from the right. So g of x, 2 from the right. You can see for the g of x, right, as you approach 2 from the right, you are still in the positive range of the y. Don't forget that when you have a graph, the y-axis for this side, the y is positive, right? For this side, the y is positive. For this side, the y is positive. From here to here, the y values are negative, and then on the x-axis, the y value is 0, right? On the x-axis, the y value is 0. So let's look at this part. So as you approach this, the graph of g of x is dipping down. We are going down, right? But we are approaching 0, which is the x-axis. But we are approaching it from the positive side. That means that this blue line is taking on values like a positive 0.00001 of some sort. So from the right, that means it's approaching 0 from the right. We will end up doing from the left too. So let's just do it here. From the left too, as you can see, with the blue line, as you approach, right, the blue line is rising and it's approaching 0, but it is in the negative region of the y-axis. That means that it's taking on negative values approaching 0. So something like it's approaching 0 from the left. So it's taking on values like negative 0.00001 of some sort. Please, are you okay? So you've done the analysis from the right and from the left. So you employ those as we go. So from the right, it's approaching 0 from the right. And then from the left, it's approaching 0 from the left. Right? So from the right, it's taking on values like a positive 0.0001. And then from the left, it's taking on values like a negative 0.0001. Please, I hope you're okay with this. Any questions on that? Okay, so then let's go back to the whiteboard and then see how this is going to pan out. So from the right, the G of S is approaching something like a positive 0.00001, something like this. And what would this be? Can anyone please help me on this? What is this?
Infinity.
Infinity. Perfect. Perfect. Positive. Thank you. So I have people agreeing. So that's infinity. I always ask this question because usually I say we need a second and we move on. But sometimes we have like about 3 people agreeing. So I always ask this. If the second person seconds, what does the third person do? That's just for you guys to see. Okay, but anyways, let's continue. So we done it from the left. From the right. So let's do it for the left. So for the left, you do limit as s approaches to from the left of f of x over g of x. Right? So for this two, we are getting like f1.5. And then as we saw, I explained that from the left to is approaching something like a negative 0.0001. So something like so. So for this one too, what do we get? You're going to get what? A negative infinity. A negative infinity. Now, as you can see, from the right and from the left are not even agreeing on a type of infinity. So that means that we can conclude that the general one, right? The limit as you approach to of this quotient is therefore dn. Please, are you okay with this? Any questions? Okay. Let me wait for some seconds and then. Anybody still need time on this slide? Okay, then let me go back to the PowerPoint. So whatever follows here is just the solution to what we did, right? So it's just giving you notes. So this is just, you see this one has nicer notes. It will refer you to the kind of law that we're using. This one is started with the sum law, and then there's a constant multiple law, and then you end up with this. I think I see something. If both sides agree on positive infinity, is that yes. So if both agree on a positive infinity, then we rather write positive infinity. And as I said, it doesn't mean the limit exists. Positive infinity still means the limit does not exist, but you rather write that, right? So maybe let me make this much more clear. So side note, right? Let me use a different color. Here I can use different colors, but on the PowerPoint, I can use different. So say you are taking a limit, right? One-sided. Say you get of say some function, right? Say 1 over s squared. Let me use a real one. This one will give you infinity. No, not 2, rather 0. 0. Let me give you a classic example. I think we saw this when I was talking about the limits, but still let me talk about this. So this one, it will give you infinity if you do the analysis thing. And then if you do this, you also get infinity. So the two sides agree on infinity. So in this case, if you are trying to ask, if you are asked to find the limit as you approach 0 in general, then that's just going to be infinity. Do you see the dynamics now? Even if there is a vertical asymptote. Yeah, so there will be a vertical asymptote as long as one of them is an infinite limit, right? At least one of them is an infinite limit. So as you know, right, for this case, from the right is infinity and from the left is negative infinity. In general, we concluded is dne. But because from one of the sides, it was a type of infinity, right? From the right is infinity. If we were trying to solve this and we got from the right of one of them, right? From the right to be infinity, then we right from here, we can conclude that s equal to 2 is a vertical asymptote. For vertical asymptote, you just need at least one of them to be true. You don't need to do for both sides. Please, does that make sense? Okay, nice. Please, any other questions here? Okay, then let me go to the PowerPoint. Okay, so as I was saying, this is just giving you nice notes, but we've already done these things, right? So sum law, you get -4. This one does not exist, so you do one-sided, and then you can conclude. And then this one, as I told you, it used 1.4, but as you can see, there's an approximation. So 1.5 is still not far off. So you are getting this. And from here, it didn't do the computation that it did. It just concluded the computation that I did. It just concluded it does not exist. But that's the computation that I showed you on the whiteboard. Please, any questions here? Okay. Anybody needs time? Okay. Now let's look at more limit laws. So it turns out that we have another limit law, which we number as 6, which is called the power law. So the power law says when you're trying to take the limit as it approaches a of a function to a power, right? Then you can just take the limit of the function in the base, right? To take the limit of the function in the base. And when you are done, you take the power back, right? You put the power back and evaluate it, right? So that's the power law. Now, the next law says the limit of a constant is the same constant, right? So for 7, an example would be the limit as s approaches a 5 of 2. It will just be 2. You see, the limit of a constant is a constant. Now 8, the limit of x as s approaches a is just a. So the limit of something like, say, s approaches 2 of x is just going to be 2. Now, why are these true? Well, for the power law, for 6, right, you can see that since the limit of a product is the product of the limit, if I have, say, for 6, this is a, let me just show you something brief here. S approaching a. If I have f times, and it goes on like n times. Then we just saw that the product law says the limit of a product of functions is the product of the limits. So that means that if you use that rule, then you can just, because these are multiplying, you can take the limit of each of them and then multiply all of them together. So that's how come you have the limit of each of them, right? So f of s, and you'll be multiplying it n times. So that's where this law is from. So it's basically from the product law, but more like a stretched one, right? If the function, the product is not just 2 functions, but we are looking at the product of several functions. In this case, n functions of the same f of x. Please, are you okay? So it's just an application of the product law, right? So that's where we get a power law. We use for, no, you won't use under the, I don't know. Are you talking about like the 6, the proof that I'm showing, or the power? No, you won't use the for technique. It's just like, say, you remember we said, so recall we said limit as s approaches a of f of s times g of x, the product law, right? We said that there is going to be the limit of a product, the product of the limit. So what I'm saying is, if you are asked to find the limit of f of x to the power n, f of s to the power n is just f of s times f of s times f of s n times. So by the product law, this is going to be the limit of each of them multiplying out. Do you see? The limit as s approaches of f of s, the limit as s approaches of another f of s times the limit as s approaches of another f of s. That will occur n times. So that's the same as multiplying that limit n times. Do you see? So that's how come we have the limit of this all to the power n. That's where the power law is from. Nice. You're welcome. So for the constant law, the limit of constant is a constant. The limit as s approaches to of x is just 2. Right. Okay. Please, anybody needs time here? Okay. Now, the limits, someone will say is getting lengthy, but I'll tell you a shortcut. For each of these limits that you are seeing, most of the time, you end up plugging in. If you plug in and you don't get a case like a non-zero number over 0, and you get a number like 2 or 3, then that's your answer, right? That's your answer. You end up plugging in most of these limits, right? So let's look at this one too. right? So when you go back, if you've been looking at what is really happened, let's just go back and let me show you something. For this one, right, if you plug in the f of s and it's giving no issues, you can just plug it in here and you add them up and that'll be your answer, right? The difference too. For this one, you just ignore the c. If you plug in a number, the c will just be there and then you evaluate the f of x. So you essentially plug, unless you encounter a case whereby, let's say it's like a number times dne or something. That's where you have to do some extra work. But most of the time, you end up plugging in, right? For these other limits, most of the time, you end up plugging in. So let me just show you this. So for this one, see, if you plug in, if you evaluate the f of s in the same as plugging in, you just plug it in and take the power. For the c, if you plug a in place of x, there's no x here to plug in the a, so it still come back as c. For this one, the limit as s approaches a, if you plug a in x, you get a, right? So don't be bothered about the fact that it's too many, but most of the time they simplify to just plugging in. But you need to know the forms because of some of the like technical situations you can have where you have to analyze, you see. So for this one too, it's just the same. See, plug the a in the x to the power n, that's a to the n, right? For this one, if you have a root, the limit as s approaches a of nth root of x is just nth root of a. What do? We are just plugging in, right? A in place of x. Now recall that we can't have an even root of a negative number. So in this case, you're assuming that if n is even, then we have the a to be positive, right? Because we can't have something like this. See, a -1. That is not a real number, right? That's I. That's a complex number, right? It's an imaginary number. It's an imaginary number, right? So we are not dealing with imaginary cases here. So we expect for an even root, we expect here to be positive. That's what this is talking about, right? Now, an extension of this radical limit thing is here. So in general, if it's not just x, but it's any f of x, then the limit of an nth root of f of x is just take the limit of what is underneath the nth root, the radical. So that's what you see here, right? And still, we're also assuming that if n is even, then the result underneath the root should not be negative. It has to be strictly positive. Well, in this case, it can be 0, no problems, right? So perhaps we should add this. Because you can take like a square root of 0 and no problems there. Please, are you okay with this? Any questions on these? As I said, don't be daunted with the fact that there are many. All of them, most of them reduced to like plugging in. Anybody needs time here? Okay. Wait, I think I see something. Okay, 1 second. Perfect. Okay, let me wait for. Oh, you said 1 second. So the second is up, huh? I'm just kidding. Just take your time. Okay. You're welcome. Hope everyone is okay. Right. Okay. Okay, so now let's look at these examples. So example 2, it says evaluate the following limits and justify each step, right? So now for A, I'll do A and then you guys can please help me on B, right? So for A, I have the limit as s approaches 5 of 2s squared minus 3x plus 4. So what I'm going to do is, the first thing I see is I see a difference and I see a sum. And then the limit of a sum or a difference is just the difference or the sum of the limits. So that means I can kind of distribute the limit through, right? So this is going to give me the limit as s approaches 5 of 2s squared minus the limit as s approaches 5 of 3x plus the limit as s approaches 5 of 4, right? Now, as you can see, the 2 is a constant. It doesn't depend on this x, right? Which we are taking the limit as we approach, right? So you can pull out the 2 by the constant multiple law of limit. So that's going to give me 2, the limit as s approaches 5 of what? S squared. Minus for this one to the constant limit, the constant rule applies. So you pull out 3, and then the limit as s approaches 5 of x. And then this one, by the constant multiple rule, the limit of a constant is a constant. So that means that's just 4. Now, for this one, as I said, the laws, most of them reduce to plugging in. So you just do plug in a 5, right? So that'll be 5 squared. And then minus what? 3. For this one, you plug in a 5, that'll be 5. And then plus 4. So in the end, you have something like 25 times 2, which is 50. Minus, that's 15. And then that's plus 4. So we end up with this equal to, so 50 minus 15 plus 4. I think 50 minus 15, that'll be 35, right? And 35 plus 4 is 39. So that'll be your answer. Now, on an exam, or when you're doing this, you don't have to show me all these rules. You don't have to show me all these steps, right? So you can just do this. Limit as approach. You can just do, you don't have to show all these steps to justify. This one said justify, that's why I'm doing it. And we just started this, that's why I'm justifying all these steps. But on an exam, that's why you master this. You can just plug it in. So the first thing you try is to plug in 2 squared minus 3 times 5 plus 4. And what is that? You get your answer, 39. You are done, right? So that's what you end up doing. But for now, we just started this. That's why I'm doing each of the steps to emphasize the rules. Yeah, please, any questions on this? Okay, then please, can you help me with B? I'll wait for your proposed answer and then a seconder, and then we'll do it together. So I said, it's always important you try these, right? Someone says, math is not a spectator course. When you're looking at it, it looks easy. But when you do it, you see where you make your mistakes. Okay. I think I'll take attendance after everything. It will be more work, but that's what I think will be best. There's an issue with when I do it straight away. So I'll look at the row. So if you're using someone else's name, please do let me know. Any answers? Or you're still working? -11, perfect. Thank you, awesome. A different answer or a seconder? And when you're done, please feel free to share your answer. Perfect, I have to say perfect, awesome. So I have several people agreeing to this, right? So let's do it together. So we have the limit as s approaches -2 of s cubed plus 2s squared minus 1 over 5 minus 3x. So as I said, with the first one, I showed you all the steps to show you how it's actually like we do it if you are justifying. But as I said, you won't be doing that on an exam, right? On an exam, when you get a limit, the first thing you try is to plug in. On an exam or a quiz or a test, just plug in. So you have -2 to the third plus 2 times what? -2 squared minus 1, right? Minus 1. And then all of what? 5 times what? -3 times -2. So what will that be? That just be -2 cubed is -8, and then -2 squared is 4. 4 times 2 is 8. So -8 plus 8, that'll go to 0, and then we just have -1 over 5. So that's 6 and 11. That's all we are done. So these ones are the cool ones. If you can plug in and you get your answer, then that's very good. Later on, you learn about these kind of limits, what they are called, right? Or what that means. If you plug it in and you get your answer, what does that mean? Please, anybody needs time here? So do we leave it? Yes, you can leave it as a fraction. Yeah, you can leave it. So on your homework or anything, unless it says approximate, do not approximate, right? If it wants you to approximate, say to 3 decimal places or something, it will tell you, the question will tell you. Yeah. Please, anybody needs time here? think I left an extra slide on the next one, but it's meant to be on the same problem, right? So you're done. Refer to previous. Okay, so as I was saying, as you can see, in most of the limits that we take, you end up plugging it in the function, right? So if you're taking the limit of f of x as s approaches a, in most cases, when you plug in the a, you don't get any issues, right? So in those cases, we call it a direct substitution property. And when that happens, we say that the function is continuous at a. We will talk about continuity in 2.5. But whenever you're trying to find a limit, the first thing to try is to plug it in. If it comes out just fine, like a 2, 3, like negative 1 over 11 or something, right? Something that is not undefined, then you are good. That's your answer. You are done. So the direct substitution property is a case whereby the function's value at that point and then the limit are the same. So all that you just do is just find the function's value and you're done, right? Okay, so that's the direct substitution. And we see that it's continuous at a point when that occurs. Now, one other thing, if two functions are equal, except maybe when you are taking the limit, they are not equal there, right? Then their limit will be the same as you approach that point. Why? Because when you are taking the limit, you're not looking at exactly that point. So if two functions are equal on every other point, except at the point where you're taking the limit of, it doesn't affect the limit. You see, that's what this property is talking about. And it makes sense, right? Yeah, please, anybody with questions on this? Are you okay? Okay. So with these up, let's move on. Anybody needs time here? Okay. So now let's try these. So we learned from the previous slide that whenever you're given a limit, the first thing you try is, it could be that it's a direct substitution property working, right? So just plug it in. So we have s squared minus 1 over s minus 1. So I say, okay, nice. This one looks like I can plug in easily. So let me try. So this 1 squared minus 1 over 1 minus 1. But what is happening? I'm getting 0 over 0. Now, this is not a non-zero number over 0. This is 0 over 0. Now, this is another type that you have to learn how to compute, right? This one is undefined, but it's a type which is 0 over 0. The numerator is 0, and then the denominator is also 0. So now, this is a new thing I'm teaching you, right? So whenever you try and evaluate a limit and you get type 0 over 0, then this is the route to go, right? The route is try and simplify the expression. And then plug in again. So that's the trick. So the kind of simplification we do will depend on the kind of function you have. Now, before we even start simplifying this, let me also talk about this, right? So note, this is just a side note. If I have a function like so, s squared minus 1 over s minus 1, right? Then that one breaks up into s minus 1. You can use difference of squares to factor out the top, right? s minus 1, s plus 1. And the bottom is s minus 1, right? Now the question is, what's the difference between s minus 1 and over s plus 1 all over s minus 1? Is this equal to s plus 1? What do you say? Is this equal to this? In the normal algebraic sense, what will you say? Is it true? Okay, so I have yes. Do you have someone agreeing to this or a different answer? Okay, so I have a seconder. So for this one, I'll say this. If you have s minus 1 times s plus 1 all over s minus 1, it is not equal to s plus 1. It is not. Why is that? Because what you're saying is, no matter what x is, they are the same. That's what you're saying. So yeah, it's true. Let's say, let x equal to say, let me say 2, right? If x is equal to 2, what do you get? You get 2 minus 1 and then 2 plus 1 over 2 minus 1, right? And is that equal to 2 plus 1? Well, the 2 minus 1 will be 1, and then that will be 3. And that, yeah, that's true. So in that case, you are correct. But if I let x equal to exactly this point, 1, what will happen? I'll be getting 1 minus 1 times 1 plus 1 over 1 minus 1. And is that equal to 1 plus 1? Well, for this side, you see you get 0 times what? 1 plus 1 over 0. And you can't cancel out the 1 minus 1 over 1 minus 1. You can't cancel out zeros when you're in the fraction. So in this case, it's false. They are not equal, right? So it fails if you're looking at the point where this s minus 1 is 0. Please, are you okay? So that's why where they are not equal. So you are correct if you say they are equal to on any other x, except at the point where this one is 1, right? When x is equal to 1, where you get 0 in the top and 0 in the bottom. Please, are we clear on that? Okay, now let me try and exert here. I'll need to create something here. Okay, let me just do this. Refer to, let me do this, shift. Refer to slice. Okay, so let me go back to the whiteboard. So this is example 3. Example 3. So we are talking about this one. Okay, so now I just talked about the fact that s squared minus 1 over s plus 1, s minus 1 is not equal to s plus 1, right? But the next question is, what about s minus 1? What about this? The limit as s approaches 1 of s squared minus 1 over s minus 1. Is this equal to the limit as s approaches 1 of s plus 1? Well, in this case, this is true. The answer is yes. Why? Because looking at these two functions, right? Let's say the first function is s squared. I mean, that's not how you're going to solve it. I'm just explaining everything. I'll write how you're going to solve it very soon. So suppose you have f of s equal to this and g of s equal to this. Then these functions are equal except at x equal to 1. Do you see? Except at s equal to 1. So they are the same except at s equal to 1, right? So that means if you are taking the limit as s approaches 1 of these two functions, then they will be equal. Do you recall this rule? Right? So it's the same as this rule. Let me show you. It's the same as this one. This last rule, this one. So if two functions are the same except at a point, and you are taking the limit as you approach the point, then the two limits are the same, right? Because for limits, you are not looking at the point where they are not the same. Maybe where one is defined and one is undefined. You're looking at the neighborhood. So as long as they are the same in the neighborhood, then their limits are also the same, right? So that's the emphasis. So one takeaway from this is, whenever you are taking a limit and you're approaching a point, and let's say the function will be undefined at that point, right? But it is defined in the neighborhood, you can always cancel them out. You can always cancel them out. So how do we get from here to here, right? We get from there to there because if you have limit as of s squared minus 1 over s minus 1, then this is going to be limit as s approaches 1 of s minus 1, s plus 1 over s minus 1. For here, you can cancel these out. You can cancel the s minus 1 and the s minus 1 out. Why? Because we couldn't cancel them earlier because that one, the s can be like 1. If the x is 1, then this one is undefined, that is defined. So in that case, you can't say they are equal. But for the limits, if you're taking the limit as you approach 1, we have excluded the 1 because for limits, you're looking at the neighborhood of 1. And in the neighborhood of 1, the s minus 1 is never 0. It's never 0. So you can always cancel them out. So that will give you what? Let me see, what time is it? Okay. So that'll give you, when you cancel them out, you get a limit as s approaches 1 of s plus 1. Please do get this. You're going to use this technique a lot. Now, and when you get here, as you can see, you try plugging in again. So that'll be 1 plus 1, which is 2. Please, are you okay? Do you understand this? And this was the first one. That's why I explained a lot, so that you understand what I did here, right? So the solution is actually this step. It's just this step. So this is what you do. Solution starts here. All the other ones were just explaining. So it will just be this simple. So whenever you have a limit, right, and you are taking it in a neighborhood, and the function happens to be defined at the point where you're taking the limit, you can always cancel it out, right? The factors that will create like a 0, because you won't get there. You're looking at the neighborhood, and the function will always be defined in the neighborhood. So you can always like cancel out common factors, right? Please, are you okay with this? Any questions on this? I see something. Nice, you get it, perfect. Okay, so we've established that. As I said, the solution is just here, but I have to explain because this is a first type. So for type 0 over 0, always try and simplify somehow, right? I brought more examples so that you see some other kind of simplification cases you will get. So let's go back to the PowerPoint, unless you need time. Anybody needs time here? Okay, this one seems to be a lot of stuff, but it's good. Okay, so let's look at this one. So for this limit, find this. Okay, so let me see. For this limit, I try plugging in. What do I get? 5 squared minus 6 times 5 plus 5 over 5 minus 5. What am I getting? I'm getting 25 minus 30 plus 5 over 0. And that's 0 over 0. Oh, this is a type 0 over 0. So what should I be thinking of? For type 0 over 0, I know I have to what? I have to simplify the expression somehow. So if I have a quotient, then the only simplification that comes to mind is to what? Is to factor. And then let's say cancel out some common factors. So I have limit as s approaches 5. So let's try and factor the top. So what is the top? For this quadratic, I need two numbers whose product is 5 and whose sum is -6. And those two numbers are -5 and -6. Let me see, I hope I have some time. Okay. So I factor this and I have s minus 5 here, right? Now this s minus 5 term will be 0 at s equal to 5. But don't forget, for the limit, we are not taking, we are looking at the neighborhood of 5, not exactly at 5. So the s minus 5 term will never take on 0. So that means it's always safe to cancel these. So that will reduce everything to a limit as s approaches 5 of s minus 6. And as I told you, with this method, you also try and simplify the expression and then plug in again. Right, so at this step, I'll plug in again. I get 5 minus 6, which is -1. I'm done. Now this time it came out perfect. It didn't come out as 0 over 0, so that's perfect.
Hey Matthew, is it x minus 6 or x minus 1?
Oh, sorry. Thank you. I made a mistake.
Yeah.
Let me escape. Yeah, I made a mistake. I was looking at the 6 when I wrote it down, the -6 thing. Draw. I have an eraser here. Sorry, this is 1. Okay, so this is 1, that is 1, right? And then that's 5 minus 1 is 4. Perfect. Thank you so much. Okay, please, any questions on this? I think it's 49. The other one will require some time, like some more work. So anybody needs time here? Yeah, this is the next one, but that's it for today. Yeah, that's it for today. So I'll end here. Next time on Monday, we'll continue from here, right? And then we'll move on. Please, any questions on today's section?
Thank you.
You are welcome.
Have a good weekend.
Thank you. Have a nice weekend.
Nice seeing you guys. See you.
Thank you.
You're welcome.
Okay, bye Matthew. Thank you.
Bye, Danny. You're welcome. You're welcome, guys. You're welcome.
Thank you.
See you.